So as you can see by my video setup problems, clearly the demo gods are not having a good day. But we'll try this content anyhow. There's some interesting learnings here, and I'll yeah. So oh good, the battery's dead too. That's no, it's blinking. It's acting. Oh, I see. No. Okay, let's clicker not. Okay, not the clicker. It's good. Okay, that's not good. Ah, I know what's wrong. Clicker is not the problem. Focus of the mouse is. Okay. Score. Hi, my name is Brad Nelson. Yes, Brad Nelson. Okay. Here to talk to you about attempting to use Chromecast in captive networks. That part works. It's the other part which we'll talk about briefly. So there's a bunch of terminology here, and unfortunately, at least my take is that networking terminology is dreadful. It sort of doesn't say what it means, and so we'll go through the terminology, but take it for what it is, sort of bad terms of art. So a Chromecast is well, there's a type of device called a digital media player, and the idea is that at least the general idea is that you have something like this lovely projector, and you plug a device into it, and it allows you to take your various sources of audio and video and images and display them on the device, and use that as an interesting surface in which to present things. And it's meant to connect to a range of different things, YouTube and other sources, various streaming services. And there's a variety of things in this market. This is just a small subset of them, but these are some of the more popular ones. And in particular in this talk, we'll be talking about a Chromecast, because I and several others, it seems, happen to have a number of them sitting in drawers in various places, because they're shockingly cheap. So anyhow, so Chromecast is Google's entrant into this space, and it lets you do a bunch of different things tethered to this cast icon. There's a whole SDK and a process for you to actually have your app speak directly to the device, and we'll talk in a moment how that works from a networking point of view. But the idea is basically, I have a thing over here, and I want to put it up on my screen and show it off in various ways. There's a number of generations of them. In fact, we have several of them present in this room. This is the first generation one. I've got one sitting here. Dennis, of course, had another one. Dennis, out of curiosity, why did you happen to have mine? I was given for free at some point at random. Yours?
I cut the cable.
You cut the cable. Well,
this was my first step into cutting the cable.
Indeed. Okay.
Is using Chromecast. I ended up at Roku.
Aha.
That Roku was a better alternative.
Mm-hmm.
Well, we're probably going to end up going back to cable.
Indeed.
It's just too much.
Oh my. I don't know whether to be excited or depressed by that.
Yeah.
So in any event, here was round one. If you wouldn't mind, here's the second generation one. If you got yours sitting there, yes. You have two of them. Oh, good. Physically on you at the moment, that would be impressive.
Well, I probably have 4 at home. This is 3 more at home.
So.
Why so many? We have that many TVs. One for each channel.
Maybe that's why I don't have any.
Yeah. Indeed. So this is the second generation, and amongst other things, so this generation has all kinds of fun heating issues. They packed all the electronics really tightly. It gets very warm. It's kind of scary. The new generation, they've separated things out a little bit, and they give you the choice of color, because and around shortly thereafter, they came up with an audio-only version of said device. You'll notice the clever record-shaped. Yes. And then they've just recently come out with a newer model. And the primary difference with this one is that it supports higher resolution displays. And the subtle transition from the Chrome logo to just branding it with Google. Yes.
Does it have a separate power adapter?
So they are, yes. So we'll get to that in a moment. But in fact, they all are sort of separately powered. You're probably wondering, yes. In fact, aha, the next slide. So they're all basically of this style. There's a little bit of little bit of change in all of this. So They have an HDMI port on one end. They have a reset button invariably. They have a little LED that tells you what their current status is. And then for all but the very most recent generation of them, they have a USB cable as the power source. And you can, we'll talk a little bit about how they're configured in a bit, but the USB cable is sort of actually primarily just for power. So the basic idea is that all these different sources just go, let you target the device. But the sort of cool aspect of these is that there are a number of circumstances in which rather than whatever source that you're, if the source that you're using is, say, your laptop and you're playing YouTube, it's very roundabout to have the video go to your laptop and then from your laptop to the Chromecast, as it is a network-connected device. And so the idea is that instead, control signals can go from your device to YouTube to inform your device to send the stream directly to your device. So this, of course, presents a huge challenge if you're in an environment like the one that we are in, a so-called captive portal. So a captive portal is like what you find at Stanford, for instance, or a Starbucks, where before you can do anything else on the network, there's some action you have to take so that you can have you can sign whatever EULA or terms of service or whatnot that they've put up for you. In some countries, this is actually, as I understand it, mandated by law. There are places where you can't just put Wi-Fi out for free, but rather the provider of the Wi-Fi has some legal obligations in terms of the folks that use it. And so my general understanding is that this was until recently true. For example, in Germany, they very recently changed the law apparently. So how do we cope with this? So what is a captive portal? It's a network that requires a login and or a landing page, and used for all these reasons: payment, authentication, EULAs, liability, or also timeout. One thing that we've all encountered in this room is that Stanford will let you stay on for a little while, and of course they don't want you to just run on this network forever. They would like you to occasionally take some human action in order to continue to use the connection, which causes Dennis trouble every single time we're here. What we would like to do, or what I would ideally like to do, is plug in this device here, and then go through the captive Wi-Fi and have it reach the network, because recall, it needs to be able to talk to the outside. And in fact, it's not just for this case of redirecting something like a YouTube video directly to the device that it needs to go to the network. No, it wants to talk to Google servers under all circumstances, and so it simply won't actually get to the point that you can configure and set up the device without this path. I should point out that at this point that the dance that it does to get set up is kind of interesting, and is similar in style to a number of Internet of Things devices. Initially, when the device is activated, if it hasn't been configured, it actually creates its own Wi-Fi network of a name with a random ID, and a number of the different utilities that you can use to configure the device will go looking around. Oh, am I in a space with one of these devices? Let me go and attempt to configure it. But typically, what you do is you'll then set up the device, at which point it will then attempt to connect to whatever network. Actually, backing up, one issue. So my understanding is that Amazon actually has a slightly better solution to this, or a more sophisticated solution, which is that in the event that the device, so with the Chromecast, you'll be asked for when you're configuring it, you'll be asked for things like login information for the network. Which of these various Wi-Fi networks around you do you want to log into? What apparently the Amazon Fire Stick does is that it actually, because there is a remote that you can talk to the display with, in the event that all of this fails, it will pop up a small browser that will let you actually attempt to interact with the captive portal and let you do the login. So a little more software can go a long way, it seems. So, of course, looking for a solution to this problem, I turned to another piece of hardware I had on a shelf somewhere, this WRT54GL. As I mentioned previously, one of the other things I've given here, there's a fun sort of open source story behind this one, which is early days Linksys actually went ahead and used a number of GPL'd programs on the router And folks actually noticed that, hey, you haven't actually open sourced all of the different things that you have used. So this is an example of the open source community having harassed them and gotten them to cough up their GPL software, which in turn led to the development of a thing called DDWRT, which is an open source piece of router software that you can install actually on now a range of different devices if you're unhappy with the range of features that you have out of the box with your particular router. And it's nice because it's sort of homogeneous and the same in various ways. And because it can do sort of all the advanced and interesting things. So, well, one of these here. The basic idea is that what I would like to do is, so you'll notice that in this environment, you're all able to easily connect with a laptop to the captive portal, click the thing, and everything's fine. But this device doesn't know what to click. So what you would like to be able to do is engage in a little bit of deception, let's say. And so every device that connects to a Wi-Fi network has something called a MAC address. This MAC address is a 48-bit number. There's actually some extensions that make them larger, but it's a unique hardware identifier. Part of it is the vendor ID, and a part of it is random to the device. As it turns out, devices can lie, and in fact, a number of devices are easily reprogrammed to lie about their device. And one potential path is, of course, you could set things up with your computer and then have it lie about its MAC address and then pretend to be the same MAC address as the Chromecast. But of course, that would be a hassle because then you'll have to change the config of your laptop and all of that. So there's another path here. So you can log in this way. What you can do instead is interpose the router in between. And the router, of course, can have a MAC address of its own, and it can log in. Now, if only you could use your computer to do the clicking on the login of the portal, and then in turn have the router route connections from the Chromecast to the network. And as it turns out, you can do this. You can engage in this pretend in which the router, as far as it knows, is connected to a single device, but your computer and your Chromecast or any number of devices can be directed through this one device. So let's talk a little bit about the capabilities of these routers. So despite the two antennas are actually to be more robust in the signal that you receive. The device is actually only capable of being tuned to a single frequency. And in the sort of classic space of frequencies for Wi-Fi, of course, there were only a limited set of channels, and although there are these some 14 channels in our country, only the ones I believe down to 11 are actually usable, and they overlap, and so in practice there's a very small number of these channels available. However, I thought I had another slide on this. Very recently, there are a number of new chunks of spectrum that have been opened up, which is delightful because there is now a much larger range of spaces available. Unfortunately, not all the hardware out there supports this, and in particular, this device happens to be limited to this particular range. Fortunately, almost all of the hardware that supports the sort of the new and the old, what it actually does is it will open up two networks, one in one of these new frequency ranges and one in one of the old frequency ranges. I was sniffing around my neighborhood, which is historically, full of congestion from various neighbors all fighting for a limited amount of spectrum. And to my shock, only a very small number of them are actually using any of the newer devices, and they are, in fact, on older devices from about 4 years back that fight over this very limited space of spectrum. But things are improving once we get to these new devices. One reason, of course, that the old set of spectrum was slightly nicer is it penetrates walls a little bit better, which may be the other reason that I'm seeing my neighbors less on the higher frequencies that are available. These were nice because you can put one router and then have them punch through. So in any event, the reason I'm talking about channels is because there's this constraint. If I'm going to have this device pretend to be a device on the network, I have a problem because I would like my laptop and the Chromecast to be able to connect to it. on a different Wi-Fi network because they can't be, on this network. And so the limitation, and this is actually similar limitation on the ESP8266, actually ostensibly can do all this, although I didn't have the courage to go and attempt to configure one in such a way, is that you, on a single channel, say channel 6, you could have multiple different networks. And so you could have this device talk on channel 6, log into Stanford Visitor, also on channel 6, but also have its own network with a different name available, also on channel 6, but sharing that channel, because you can overlap these. And then the notion is that within, from the point of view of the network, you need to, of course, then isolate things into their own subnet. And so there's a bunch of different pieces of reserved subnets that you can use for your own network. Typically, there's ones of different sizes, and typically, sort of home-scale routers assume you're not going to have more than 200 devices, and so they frequently will use Class C in the 16-bit range. And so what you can do is configure, for instance, I've set this one up to use 192.168.3.1, and so it's got a separate range that looks very different than the range of addresses doled out by the Stanford network. And then you can do something called network address translation. And the idea is that basically the router is pretending to be one device, but whenever a TCP connection is made, it will take one of these connections on its local subnet, and it will open that connection on the single shared IP address and pick a unique port to bring that connection through. And so you're essentially, again, sharing that one IP address that's been doled out to you by the Stanford network to service all of the traffic on your local network. And so Stanford can be in whatever its particular subnet is, and you've got your own separate range of IP addresses provided to the devices such as the Chromecast and the laptop. But from the point of view of Stanford, it's sold out one of these single 10.something addresses to FIGI. I actually haven't looked what Stanford uses. I made these slides when I was not physically here, so I don't know what class of network Stanford is using. And then, of course, there's this is where a bunch of the fun terminology comes in. So in the parlance of routers, which is, as far as I can tell, is not entirely universal, but I'll use the parlance of DDWRT. There's all these various different modes of operation. And so there's a thing called an access point, which is just your bridging from Wi-Fi to wired, but that assumes that everything is sort of open, and that's not quite what we want. Yes.
That would be like that device right here. No, see where I'm pointing?
Yes, indeed.
Right underneath. That would be an access point.
Quite. So then there's the notion of a client device, which will let you connect a wired router to another Wi-Fi router on a separate network. A client bridge, which does the same thing, except that you're on the same subnet. An ad hoc is another mode, which we're not going to go into. But the one that we're interested in is, in particular, a repeater, because it allows you to have a separate virtual network that is connected over Wi-Fi to another network. So too many terms, and these are shockingly similar, and things that you would think would just be a bit one direction or the other have to get a name for some reason. And then what you do is, within that mode, you're allowed to have your primary physical interface and have it be Stanford, for example, and then you can set up a virtual interface, a second name to connect to. And so right now in this room, or actually once I plug this in the overtaxed pile of stuff here, there's now both the Stanford network, and then this box has a network called FIGI, and it is also connecting as a client to the Stanford network in order to actually provide a path to the internet. And then you have to provide login information for each of the different networks. So in the case of Stanford, actually, you would provide no login information because it's an open network. And then I have a password on this router so that when you connect to it, you're reaching the network indirectly. One other sort of nuance here is that, if you'll recall back in this picture, because you're providing your own subnet, you need to dole out IP addresses to the different devices that are present. because Stanford is not going to, it will dole out its one IP address to you. It's up to you to dole out these. And so you need what's called a DHCP server running, and this is, of course, provided by the router. And it offers to dole out IP addresses to each of the devices in a little dance over UDP. So you need to have this turned on. So let's briefly talk about, before I go to the demo, which is less than I had hoped, but more than nothing as I had before the break. Let's talk about some of the alternatives. There's a range of different routers that can do this. I've shown DDWRT because it's sort of standard, but you buy an off-the-shelf router frequently, there is a setting buried somewhere that can do this kind of thing. There are some routers that are specifically advertised to support this now, because this is the typical scenario is I've got my streaming service and I want to go to a hotel room, and the hotel has captive Wi-Fi, and it's the same problem. So they'll sometimes be called apparently WISP, wireless internet service provider routers, or travel routers, and they'll be advertised as sort of this being the default mode of operation for them, and made to be sort of convenient. Yes?
Question, so this your travel router, so this one not necessarily connect to the real, internet, right?
No, this is connected. This is because it's connecting to Stanford, and from Stanford to, yeah, yes.
But you are not manually connect to the,
No, yes. Yeah, and so the key thing here is that, and we've hit this with a number of these Internet of Things. Actually, we'll talk about that in a sec. Actually, in the next slide. So this is useful, of course, for this sort of thing, like with Chromecast. But a number of the playing around that we've done with Internet of Things devices, we've had the problem that we can set up a router and devices can talk locally, but we're not actually connected to the real internet. By having a router that can talk through Stanford's Wi-Fi as a captive portal, we can have a number of devices interacting here, but they could also reach the actual internet through the router through to Stanford. And so in essence, anybody who's logged into this SVFIG router here can get to the internet without the step of this explicit login. So you'll recall that I mentioned the configuration phase, where initially what the Chromecast does is it opens up its own network of some random name and basically broadcasts to the world, I'm a Chromecast device. When you configure it, one of the things that you do set is, of the local Wi-Fi networks, which one should the Chromecast hang up the phone, go and call? And it's actually quite an annoying little dance, because the Chromecast turns off its local network while it goes to then attempt to connect to the outside. And so it kind of goes dark on if you're configuring it with your phone or laptop or whatever, it will go dark on you while it's attempting to connect. And hopefully you hear a call back from it essentially on the real internet, but in the meantime, you don't hear a response. And so it does have the option, of course, to let you provide the network name and also the password, but it just simply cannot cope with all of the different range of login screens and EULAs and whatnot that you might have to click through. So actually, before we go to questions, let's do sort of a minor demo. As it happens, there's an extra challenge that I did not anticipate. Despite having come here to test this, I have just learned of a thing called HDCP. And so apparently what is going on is that sometime after HDMI was standardized, a number of folks involved in the DRM community got some additional concern, shall we say. And so there is there is the bare HDMI protocol, of which this relatively old now projector is a member. A number of devices, in fact, the majority of actual televisions and whatnot that are sold, speak this additional protocol on top. And basically, the idea is that in order to have a license to broadcast in this protocol, you must be a signatory of the appropriate contracts. And then there's a little dance in which you basically, I'll show me your license and you show me my, I'll show you my license and you'll show me yours, and then we'll be convinced that we can talk to each other. Otherwise, what you get is a black screen. Now, what I will almost certainly try at some future date is, as it turns out, yes?
I've seen that actually on a monitor running Amazon Fire. And I got a black screen. I was like, what the heck?
So,
and then I plugged it into a monitor that had the right configuration.
Indeed. So it turns out that this protocol while it has been sort of marginally successful at, only marginally successful at actually preventing piracy, because people are going to pirate, right? But in any event, what it has succeeded at doing is making it difficult to connect devices. There are a number of devices out there that are apparently on an ongoing basis sold for routing between HDMI devices. And frequently these devices, shall we say, have flaws in them in which they don't actually check the handshake all the time, all the ways. And so apparently a number of folks have learned ways to find one of such blessed HDMI connectors and converters and plug things through that, in which they will provide the notification needed on the one side and happily ignore the lack of it on the other. And so I will probably go searching for such a device in the near future. Apparently this is not illegal, because none of this is actually something that was part of the original contract with HDMI. It's just that if you want to talk the blessed dance, your device needs to do this. My guess, and I've heard that this is the case, that if I were to push the firmware reset on this device, so I recall at some point in the past, for example, being able to connect to this device, not to the network, but successfully to this display. I believe what was going on is that when this device first came out, its firmware did not speak the blessed dance, and was able to, therefore, talk to this older projector. However, at some point, they've done a firmware update so that it can talk the blessed dance, and therefore no longer is able to talk to the projector. So,
unless
yes.
you get a filter between
Yes. And, yeah, so the issue is that the filter needs to be smart enough to lie to the Chromecast that I have the proper certificate, but happily ignore the fact that the projector does not do this. Technically, such a device is not supposed to do this, but if it is not a device like Chromecast that can be updated in the wild, what you're going to do if it's broken, right? Yeah. So that's apparently where it's at. On top of this, as I understand it, the keys to this little dance have apparently already been cracked, because people are quite clever, and apparently encryption is hard. So there we are. So let's go and let's experiment with Chromecasting here a little bit. So now, so as I said, I'm not actually able to successfully connect the projector, because if we go to the other screen here, well, I will show it briefly. You get, well, actually, this isn't plugged in. You get black. Come on, black, black, black. Oh, actually, I think it has to be. Sorry. Yeah, it's the other screen. Yeah, it's black. So, whoop, there's the black. So, however, as I discovered at the break, I happen to have on me an HDMI, and actually the interesting thing is we tried several combinations here at the break, including plugging in directly and through the cables before I did the research at the break to learn this business about HDCP. I also have this converter which sits in between to go to VGA. However, it turns out that apparently this converter is not appropriately blessed to also speak the blessed dance even when going to VGA, and so as a consequence does not work for that facility. However, it does split out audio from the HDMI cable, and audio is a whole separate matter, and so I will at least be able to demonstrate audio going through. If I can get back to the laptop to show. Oh, is it not? There we go. Okay, so let's go to YouTube to start. So ideally, what we would be doing with all of this. By the way, you may ask, what is the point of all of this? I think that's the account we'll do. Okay. So you may ask, what is the point of all this? Well, one potential usage that would be very nice is that Dennis frequently broadcasts these things over Hangout on Air, and if we had the Chromecast, it would be relatively convenient for us to just run a Hangout here, because you can also have a Hangout broadcast from the Chromecast device, and then folks would be able to wirelessly project their slides to the Hangout, have them appear up on the display. It would all be beautiful, at least in theory. So as I said before, this device is not going to be able to successfully cast video, but I will be able to cast audio. So the way that this works, where am I? I'm not getting the, hold on, is that I can cast the page, and I want to cast YouTube. Okay, it's not finding the devices. Ah, I know why it's not finding the devices. It's not finding the devices because I am not on the FIGI network, because this machine was, so step one is that where I'm currently connected to Stanford Visitor, I need to connect to FIGI. And I need the password. Whoopsie. I lost my screen. Let's see. Let's try again. Okay. And so I need to put in the, this is what I'm putting in is the password to this router. And did I just lose it? Oh, hold on. Yeah, okay. Come on. Oh, come on. I'm going to close YouTube because it's aggressively trying to touch the network and therefore is eager to go back to a network where there's a Wi-Fi connection. Oh, come on. All right. I'm going to, apparently this page does this as well. So let me close all of it and see if that will. Come on. All right. Go back to FIGI. Okay. Disconnected from Stanford. No, I don't want to be connected to there. I want to be connected to FIGI. Connected to FIGI. Aha, okay. So you'll notice that, actually, let me do this on a different pro. So, okay. So separately, of course, in the category of demo file, my laptop is also making a fun noise, which I'm assuming is the fan having died on it. So now if we go to, let's sign in. Okay. Anytime now. Okay. So let's suppose that we go back to Bach here, and then we should see the ability to cast to no casting devices found. This is not. Wait, are we on FIGI? On FIGI. Actually, we can confirm we're on FIGI by actually going to the router. So we can actually connect to this router, and you can see, in fact, we'll be able to see the Chromecast here. Aha! So connected to the router, we have the laptop, we have my Android phone, and we have the Chromecast. So for some reason, my laptop is having a hard time talking to the Chromecast, so I will instead use my phone, which is also connected to the Chromecast, to my phone. So I've got YouTube up here, and I'm going to go ahead and add that actually, and connect to here and play, hopefully, the music. Come on. Yes. Okay, here we go. Connecting to SVFIG. And that's getting really annoying, so I'm going to close that lid. Oh, that's not going to do anything good. Actually. Okay. Playing on SVFIG, why are we not hearing it? Maybe it's I tested this moments ago. Apologies. Oh, I know. No? Okay. So, all right. So we have the phone talking to the router, or sorry, the phone talking through the router to the Chromecast, which talks back through the router to YouTube, receives the audio through the router, and plays through to the device. Ideally, we would be seeing a video to go with it, but we are not.
So next month you're going to show your slides from your phone?
Maybe. Well, next month at the very least, I'm going to see if I can overcome this video problem now recognizing that there is such a problem. And of course, the lesson is test on all the exact hardware, even down to the projector, even when you think it's the same. Yes, indeed.
So when Chromecast is connected to the internet, does it force update
Yeah.
to the
How do I get to a colon? Here we go. Colon. What's it? The password is colon square dupe star semicolon.
Google push new firmware automatically to the device?
Yes, Google will update your Chromecast.
Let me see if you can. See if you can cast. Let's see. Okay.
It says updated. Dennis, did your Chromecast get updated?
Okay. To SVFIG. Okay.
After it's plugged into the internet?
Some music, I don't know.
See, his got updated when it
On
was connected.
some music.
I'm sorry. I got drawn into the logging in. Sorry. You,
We're just talking auto-updating firmware so that it
keep it on the old version.
right.
My guess is that the Chromecast would be. So now he's. I know. Yes. So my guess is that the firmware, the Google will probably not be willing to talk to the device if it hasn't updated its firmware. So that.
So, if you're at Google and you're in a meeting with a bunch of guys and you want to let the next guy put his laptop up on the big screen, or I guess his phone or his tablet or whatever, what happens?
So.
Are y'all using Chromecast?
What we actually have set up is these kiosks that are similar to an ongoing Hangout. And so what happens is that you'll just connect to the Hangout and you can present your screen and thereby present that way. And that's essentially what it is. So the step after this would have been to say, okay, let's Chromecast a Hangout to the screen and then just let whoever wants to connect to the Hangout. They can share slides, they can share their screen, they can share what they need, and then. Yes. Well, it can go out. It can be the very same Hangout that Dennis is broadcasting to.
Yes, but I'm just thinking from a company at work sort of standpoint, you don't want all your stuff going.
There are access controls on it, and so for by default it is limited to folks coming in from an internal address. But there is actually a way for us to allow outside folks to connect in because sometimes we'll discuss things with outside folks, and so they can use a Hangout to have a shared meeting with all of us. So.
I've seen meeting rooms that have these little hockey pucks plugged into your USB, and when it's your turn to put your laptop up, poke the center of the hockey puck, and as if by magic, it becomes a display adapter that goes over the radio, some radio, Bluetooth, 3.2, straight to Wi-Fi, I'm not sure what, to the big screen.
Indeed.
And Sony TVs have all this stuff built into them.
Yes, indeed.
You can sometimes maybe connect to it. I'm not sure how.
There's a number of entries. There's a number of different entrants into this space and a number of different techniques. And I think the struggle that all of the various companies in this space are having is sort of how to make it work seamlessly and nicely together. And the trouble is they're each sort of slightly different in how they work. And we're in interesting days in that regard.
The answer is easy. Just like Microsoft, leave it everything open.
Indeed.
Everybody will connect.
Everybody.
So, some of you may ask, what's this got to do with Forth? And the answer is I dragged Brad into this because I thought it might move the ball forward in terms of what we do here at our meetings and how we get things up on the screen. And he mentioned some stuff about remote presenters and blah, 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 blah. So, blame me, it's my fault. And if you want a strict Forth meeting, this isn't it. So, ready to wrap it up?
I am indeed, unless there are any other questions. Oh, there's one.
Could you dump the firmware of the Chromecast? Is that possible?
I have not attempted this. It is entirely likely that it is possible, but my guess is that there are measures in place to make this challenging, but all things are possible.
It's never likely you can go back. The thing is people create it, people can uncreate.
Indeed. Well, as for example, this protocol between the HDMI devices, it seems that secrets don't tend to stay secret for very long, and/or encryption has challenges.
Along with the originally the scramblers, which have the same concept, right?
Yes.
They scrambled the video, but the audio came through.
Right. Right.
And now then we had the DVD, with all the keys. They got out onto the internet.
Yeah. What's that?
I don't think it's a problem of projector.
Oh yeah.
Because it's an analog input.
So no, but the issue is the Chromecast. Yes, the Chromecast is refusing to send a signal because it is not getting the handshake from the projector. The projector is old. The Chromecast.
So there is analog to digital conversion.
Yes.
That box.
Yes.
That's the problem with that box.
But the issue is I don't believe that it's any of this. I believe this is old enough that it doesn't do the dance. So we could actually try. We could try an interesting experiment, which is I'm told that if I do a firmware reset of this device, which I will now. Oh yes, please come up to plug in. I'm going to try a firmware reset because we'll get to see an interesting thing here. So I'm told that on a firmwhere reset, this device may go back into a mode where it's happy to, and you're going to want the connection shortly, so where it's happy to, where it does not speak the protocol. And in that case, then the Chromecast may try to protect something, but we'll see if that happens in all of 2 seconds while it. Let's see. It went black. I'm not seeing anything. Something. Yeah. No. Something. You see there. So now it's projecting because I have factory reset it. The issue is that what? No, but it's not going to stay because what's going to happen is right. It's going to do this, and so the issue is that right now it's in factory reset. So this is before the magic handshake protocol. So now the Chromecast is happy to actually send signals on to the device, but then what will happen is it will almost certainly attempt to. It did the update. Yeah, okay.
The G was the update.
The G probably was the update, at which point it is now, yes.
Is there a way to change the vendor ID and product ID of the Chromecast so they will not recognize it as a Chromecast?
So again, it's not the projector that is rejecting the Chromecast. It is the Chromecast that is rejecting the projector. You see what I mean? The Chromecast is saying, here's my certificate. Where's yours?
To prevent it from doing the software update.
Again, I think the issue is that we very much need the Chromecast to be able to talk to the cloud, at which point it's going to want to have the latest firmware, at which point, yeah.
Just look at the USB and see if the Chromecast plugged into your USB port.
It's HDMI.
It's a much better
Anyways, please unplug me here.
the way around $20 items.
So, you want this bit, or do you need a converter? Oh, you got the converter. That's pretty tight. All right, there we go. Let me get all of this junk out of your way.
Well, it does in the right direction. Spoofs the handshake.
Yeah. And it's, by the way, I should say, my understanding is it does not willfully spoof the handshake. It's that it has a flawed implementation of the handshake. Because recall again, it's not that you want a device that completely ignores the handshake. It's that you need a device that will happily give its certificate to one end and ignore the fact that the other guy did not provide one.
Good, very good. Hopefully see you working with the video next time.
Indeed.
Almost there.
Almost. Inch by inch.
Question next would be how many of all those vendors going to that protocol?
My understanding is they all have a sort of an incentive to go to that protocol because if they do not participate, they can't plug in, right? Because everybody, it's a sort of a suicide pact, right? If you're not part of the part of the club, you can't. I'm assuming that's why Chromecast, which initially had firmware that didn't do the stance on this old version, has gone to talking the protocol because otherwise it wouldn't work with all the new DVDs. What's that? I do not know offhand. I have not looked. My suspicion is that it is. I'm sure there are. I would be surprised if there wasn't some portion of it that is, but my guess is that it may not be in a form that's easily leverageable for.
It's running Android, actually, not Chrome OS.
Yes. Hi, my name's James Bowman. I'm going to be talking about reading and writing Flash on the GA144. I have stood up here a few times over the years talking about the GA144, and I must admit I put it to one side for a couple of years until Michael and Mark pinged me last month and said, what about that GA144? So I got it out and I started hacking on it, and it's all kind of come back to me. So I've decided that the first thing I wanted to make it do this time was talk to its onboard flash. And I'll talk a bit at the end about why that's an important step and where that takes us next. But it turned out that writing and reading Flash was kind of a project. It's kind of tricky. And I'll talk a bit about what happened when I tried to do it a couple of weeks ago. So I guess a lot of people in this room are familiar with GA144, but I see a few new faces. And people out there on the internet ought to know about the GA144 because it's fantastic. It is a chip from a few years back now, I think 2010 maybe, and what it is a CPU of a sort. It is actually a grid computer. Each of these cells in this complicated diagram is actually very simple. It's just a small computer. They're all basically identical. And the chip consists of a two-dimensional grid of computers. There's 18 across and 8 down for a total of 144 machines. They're all sort of independent. Their only connection to the outside world for the ones on the edge is through pins, but from the ones inside, they can only talk to its neighbor. So each computer can only talk to its north, east, south, west neighbor. So you have an interesting problem of how to actually talk to the middle node, as you have to get the cooperation of all of the nodes leading to it to carry the information back and forth to it. So programming these computers is part coding, which we're all used to, and part floor planning of arranging this 2D space so that it can carry the data around. This happened a lot. In the sense, it's a computer, it's a kind of computer. It's very strange. The strangeness just begins at the hardware level and stacks up all the way up to the IDE. If you follow the tutorial on the Green Arrays 144 and keep a note of how many weird and surprising things there are at the various levels, there's dozens and dozens of exciting and odd things about it. It's an 8-bit computer. Sorry, it's not it's an 18-bit computer. You don't see that every day. The independent CPUs, these guys, are all clockless. They don't actually have a fixed clock frequency. They run asynchronously. That's unusual. The computers only have effectively 64 instructions of program memory. So
as machines go, they're very, very tiny. They all have 64 words of data memory. Also, not a lot of resources to go with. The instruction set of the computers is super minimal. There's no subtract instruction. That's an embarrassing luxury, and you have to make do without subtract. It doesn't even have a full set of fourth words. They're kind of fourth computers. They have stacks, but as Ting covered this morning, you can make a rotating FIFO into a stack, and nobody is any the wiser because yours is 256 deep. On these computers, they're 8 deep, and it's actually part of the plan, part of the suggested operation to overflow them on purpose, to use them as an 8-entry register file by accessing one at a time. It leads to some interesting code. And a lot of the recommended ways of using these computers are not so much programs as just deliberate crashes of the CPU. You can crash them in a particular way so that they carry data continuously from left node to the right node. And that's called a wire node. And I don't really consider them programs because there's no exit from this. They're in an infinite loop and they just happen to be conveying data forever. All of these things in concert, you can kind of consider to be a traditional program. Right, if you've got a bunch of nodes each doing their own thing and you arrange them in this thing in a certain pattern, they might do something useful, and that is the program, even though it's really 144 programs for these individual computers. And this is what I mean about stacks of weirdness, is that the hardware's strange, but then on top of it, if you use the Green Arrays IDE tool, that's another layer of surprising because it's, for example, it rebinds the keyboard. You have to learn to type over again. It's highly modal. It makes Vim look like a dream. Okay, I'll run through what you're actually looking at here. That's the map of the whole chip. You can see it's 18 by 8. Those are the individual computers. The blue section is an 8 by 4 window into that because on the left, those are those computers expanded, and you can kind of see that each one is showing what it's doing and its current, some of its current state. So we're looking at an 8 by 4 subgrid, and then on the right-hand side is another zoom in to one actual node, and here's its code sitting in memory. But for reasons which have never been clear, I think, to anyone, memory goes up, not down, which is why these numbers are counting down, because this is a low address and this is a high address. So if you were to pick up the IDE and you'd never seen a computer before, you might be fairly accepting of it. But if you have certain fixed ideas in your mind about how a computer ought to be, then this might challenge them. I decided that this was too much for me and I wasn't perhaps able to exercise the mental agility to deal with this, and I made an independent tool chain, because in the data sheets they do actually tell you exactly how the hardware works, and the Green Arrays people have told you how to assemble instructions and everything, so it's not secret. So you can actually make your own tool chain, your own assembler and loader to talk to the chip, and that's what I did. I made an open source one. It's a little bit of Python which assembles the code and downloads it into the chip. So then I could use a traditional editor and things like source code control and other niceties. So that's the chip. The other part of this particular endeavor is talking to Flash. Flash is kind of part of the modern world. Everything we own has got a bit of Flash in it. Flash was a great invention, but under the covers, it sucks. It's a kind of memory with the emphasis on kind of. It is writing Flash takes a while. It's like this guy. He can remove a piece of wood. It's kind of expensive to remove a piece of wood, but if he makes a mistake, if he's removed too much, he has to go get another plank. The really expensive operation. Of course, once he's cut it into a shape, then it's fairly easy to look at and say this is a piece of wood. Like that with Flash. It's easy to read. That's its strength. That's the only good thing about it. It's quite hard to write. It takes a long time and a lot of energy. And it's really slow to erase, to go back and get the new plank. So there's a lot of costs. Obviously, flash is a lot quicker than a moving platter disk, which is the thing that we'd be stuck with if we didn't have flash, if flash hadn't been invented. But flash is so far from the Platonic ideal of memory where you can read and write to a bit that it's really hard to use. But of course, it's quite cheap. The cost per bit has come down over the years, and before flash, we had to do things like custom ROMs or UV erasable EPROMs. Flash really was a game changer. It has a limited life. These planks will last a century. Flash is typically quoted in the sort of 10-year range and then maybe 20 years. But if you have a 10-year-old car, then all the flash in all its microcontrollers are reaching end of life, and that car will fail. Not because of anything wrong with the car, but because the flash has reached end of life. It is finite. It can only deal with a certain number of thermal cycles. If you read and write the flash too many times, it will get stuck, either 1 or 0. That's quoted as their endurance. And nice flash has high endurance, maybe 100,000 cycles. Cheap flash has low endurance, maybe a few hundred cycles, which is fine. If you're just making a manufactured object, it might only be updated once, and then it goes into service until the day about 9 years later when it fails. If you've got a lot of updates coming or you're using it as rewritable I/O, then you'd want high endurance flash. And for large flash devices, there's things like wear leveling, where you try to not write to the same region in a hotspot and avoid those hotspots, just to try to extend the life of the stuff. There we go. So actual numbers, if you're doing really well, you can probably write 100K a second to flash chips like this. These are single chip embedded flashes which are in everything. And they range in size from like a megabyte to maybe 32 megabytes now is a typical range of what's available to buy these. And they cost maybe a couple of bucks. The erase time is normally much longer than the write time. So you can write in a few milliseconds. Erasing might take 100 milliseconds. It's expensive stuff. And all you can do while it's doing that is just poll the flash, are you done yet? Are you done yet? The flash internally is covering up flakiness for you. So changing the flash or erasing it actually takes the flash engine multiple tries. It's like a broken piano where it's just going to try it a few more times until finally the note comes out. And that is what's happening under the cover. So the delay is variable. So you've got to poll it. Or wait what they call in the datasheet the worst case time, which is a sort of absolute worst case of how long it takes to erase the flash. A big flash might take 5 minutes to erase, worst case. So unless you poll it, you have to wait a really long time for flash updates to happen. It's super bad for consumer devices while they're updating themselves because they sit there and they say, I'm now updating my flash, don't disconnect power. That could take a really long time. They could be sitting there for 10 minutes in this sort of crucial moment of vulnerability, waiting until the flash is complete. If power is interrupted during that time, if it crashes, flash is in an unknown state and the thing's broken. So this causes a lot of failures in the world, and flash isn't that great as far as performance. And that's why there's always a few stories about non-volatile RAMs, because people are looking for something better than flash. All right, enough about flash. There's a connection on the green erase chip dedicated to flash, because one of the capabilities of the green erase chip is to boot out a flash. There's the protocol that these flashes all use is SPI. It's a 4-wire protocol with a clock and input and output lines. The SPI node 705 is dedicated. Those are its 4 IOs connected up to the flash chip. So after boot is finished, whether it booted from SPI or not, you can load your own little program into 705 to talk to the flash. This is Chuck Moore's page on how to write to the flash, which is kind of informative if you're prepared to sit down and go quite carefully through the source code. What to say about this? Well, without going into its details, is that Chuck is He's not shy about imposing a cognitive load on the reader. So you can see the ORG statement, which does what assembly programmers would expect it to. It sets the origin. What's the origin? What address is cell at? Okay, any color forth people? What address? So it's defining cell to be somewhere. What is its value? Third line down, right? Just on the. Is set the origin. See these ORG statements? It's sort of making this list of assignments. He's setting a symbol cell to be CC. So CC sets the origin. And then, unlike a regular person, he felt no need to actually line them up. It's actually on the next line. So the address of cell is CC, and the address of bits is DB. Right? What's the address of 80? C2. Yeah, it's once you get a piece of if you get a piece of paper and then make some marks on it, it all falls into place nicely. But I'd also point out some other usability issue in that when it transmits a byte to the flash, this is a primitive that everybody makes when they want to talk to a flash memory. This is an 18-bit computer. So where's the most convenient place to put those 8 bits of the byte? They're not in the low bits of the word because that's not ready to be shifted out. They're in the high bits of the word. So all of these constants, like this one, is an 18-bit number with the 8-bit flash command left shifted 10 bits, and Chuck's just done the math and written it right there, that you can just read it. What could be simpler? So using it, there's a few issues. It's just it's it's a puzzler when you first see it. But yeah, it is. It's got that advantage. So this is actually a piece of code. Where it fits in is this is loaded into RAM. This is the flash driver, and it's calling into the ROM because every node has 64 words of ROM and 64 words of RAM. And you can load a RAM which calls into the ROM, and then hey presto, it's got some resources to use. So you don't have to write everything yourself from scratch. You can call into the ROM routines. All right, well, I had my pieces. And this is how my back of the envelope design looks like. There's the PC at the top. It's got a file that it wants to put into the flash. All right, so you'd normally do it. The PC talks to the microcontroller. Microcontroller stages the bits that want to go into the flash into its RAM. And then it carries the stuff from the RAM into the flash. This is how every microcontroller with flash, this is how bootloaders work. If you've got an Arduino, this is how it works. This is the traditional thing. This protocol here is the microcontroller is defined by the flash. This is the flash command set, which they tell you about in the flash data sheet. They're all the same. The RAM is a few K, no problem. And then the PC talks to the microcontroller using some sort of proprietary command protocol, saying things like erase a page, write a page. And because the flash duration is unknown, you've got a poll for the flash. There's the microcontroller sits spinning, waiting for the flash to finish, and then sends some completion message back and forth to the PC. Simple enough. It is simple enough if you've got a microcontroller and some RAM. But the way things are with the GA144, we don't really have a controller yet running on the chip. We can program individual nodes, but we can't write programs big enough to control this whole protocol. And the other piece of the puzzle that we don't have on the GA144 is nobody, as far as I know, in the world in the last 6 years has managed to make a RAM for the GA144. It's quite hard to gather a group of those nodes together into a rectangular shape and use them as a general purpose RAM. It's not been done yet. People can make a single, but not a multiple. So things are quite rudimentary with the GA144. There's no CPU and there's no RAM. But apart from that, we're all set. So how do we do it? Well, remember when I said that the program consists of something that we put on the GA144? Decided to break it down and write a different program for reading and writing. It takes blink of an eye. It takes less than 1/10 of a second to load up the GA144 with a new program because it's RAM-based. So actually loading a program into it is super cheap. It's great. It's done before you've taken your finger off the return. So it's no problem when doing a protocol to write different programs to do different things. It can just we can just reload the GA144 instantly. So I decided to make a dedicated program for reading out the flash. Here's what the floor plan looks like. Obviously, the whole chip's unused, apart from node 708, which talks on the UART, and 705, which is reading from the flash up at the top there. And those two nodes, 706, 707, are just wire nodes. They're just carrying data back out of the flash. So 705 wakes up, talks to the flash, starts reading out its data, feeds it out to 708, which conveys it to the outside world. And there we go. We can just listen on the UART, and the flash data appears on the outside. That was easy. It's a nicety, it's a detail that it's worth pointing out that 705 might be quite slow, but because we're talking on the UART, it's fine. The UART just waits for the data, so it's kind of self-limiting. There's no problem. And there's never, even if 708 was running quite slowly, if we were talking at a really slow serial speed, 705 would just block until these wires are ready to carry the data across. That's the sort of magic of these interconnects between these CPUs, is they just block until the receiver is ready to take the next data. Okay, writing is the hard part. Can't do this. And the reason you can't do this is because there's no flow control on the UART. Like a lot of modern UARTs, it's just, there's no handshaking. I'm not sure handshaking works very well on UARTs anymore. So 708 would accept the flash data, of course, and send it down to 705, but it would overflow because 705 needs to say, hold on, I haven't finished erasing this block yet, or it's taking longer than I expected. So you could, I guess, send it down really slowly, maybe a byte at a time, with a really long delay between each byte, and then each time you reached a 4K boundary when it has to do the slow erase, have another delay, and this would take hours. Could do it that way, and that gets away from the problem of handshaking and this back pressure on the delay. But really, to do it properly, what you've got to have is some storage on the chip. You've got to put the 4K on the chip, and then it writes the 4K out into flash in its own good time, and then tells you when it's done. This is the best way of doing it, but how do you do it when you don't have all of that infrastructure like a microcontroller and a 4K RAM? Well, so made a new kind of node. So nobody knows how to make a big RAM yet, but I was thinking along the lines of how to make something simpler. So the first thing I thought of was maybe a shift register. We can make shift registers and then just put them in a line. And those shift registers, like an old delay line memory, you could imagine a really long set of them constituting 4K of delay line. That led me to make something even simpler, which is just a node with some data in it, which streams on out of its output and then becomes a wire. So you've got a node which has a tiny little program in it, which dumps out all of the contents of the node. And when it's finished dumping those 60 or something words, it just becomes a wire. How is that useful? Well, those are wire nodes across the top connecting those two. And this long serpentine thing are recite nodes, and that's why they're drawn a little bit thicker, because each of those nodes is one of these recite nodes. What it does is it has about 60 words of storage in it. First thing, 704 to the left, streams out its contents, its 60 words, and then turns into a wire so it can carry the next upstream node. And then it's 703's turn to dump out its contents. It all comes out down the toothpaste tube into 705, and that's how the 4K gets into 705. Okay, now, if you do the math, then there are 33 nodes, so I just laid out 33 nodes like that in this serpentine path. At program load time, the contents of those nodes get set to the 4K that we want to put into the flash. We send that into the machine, into the GA144. It runs. Data comes into 705, the 4K, and then when 705 has finished writing the flash, which might take 100 milliseconds or something, it just sends a completion message, a single number, back up to 708, and then the microcontroller can know that the 4K is finished. So the whole process for loading 4K is construct a program, load it into the GA144, wait for the completion message to come back, and it's done, and it can load the next 4K. This takes a little time, about a quarter of a second, to actually do that whole cycle, but just repeating it for every 4K in the whole image is no problem. All right, so now the actual code, and this will give you a flavor of what it's like to use GA144. Okay, so the first thing it does is push 4 constants onto the stack. Source and dest are the source and destination nodes. They're the addresses of our neighbors, either north, east, south, or west. The constant 3, which are magic number I'll come to in a moment, and likewise 60, those things get pushed on the stack, and then this next instruction here, push, is pushing the number 60 onto the R stack. It's a dual stack machine, just like we're used to in fourth. Unlike a usual machine, there's an A and a B register, and this sends this next number 3 into the A register, and then this B bang puts dest into the B register. So in this little program, A is a source and B is the destination. That's the setup for this node. This next part is the actual main program of the node, and this is what actually gets put into node memory. This is what gets executed, the program proper. So first, fetch at plus fetches from what the A register was pointing at. Now the A register was set to 3, and what's not pictured in this slide is the rest of the 64 words. So that's word 0, that's word 1, that's word 2, and then words 3 through 63 are the data for the rest of the node. So down below here, you can imagine all of these just raw bytes sitting in memory. So it fetches from 3 upwards, writes it to the B, which was the destination register, and then UNext is a looping construct. Remember we pushed 60 on the stack earlier? It really means UNext means repeat this thing 60 times. And it's super fast, it's super economical. It's kind of the nice part about using GA144 is when things fit in a small loop like this, it uses very little energy to actually do these things. And this whole thing, this sort of memory copy, has taken effectively one instruction slot. This is 18 bits of code that it's taken, so it's super compact. After it's done 60 copies, this is the recitation is complete, it wants to turn into a wire node where it copies from source to destination. It wants to just ferry traffic. So it writes the source value, which was still on the stack, into the A register, and then goes into this infinite loop, this wire loop, where it reads from A, writes to B, and then jumps back to wire. And that's it. It's crashed effectively, continuously ferrying its data along, but before it did so, it copied its contents out into the downstream. They all run like that. So 704 dumps first, and 604 right on the very tail end dumps last. So all 705 has to do is read from its west port, and it gets this whole 4K of data coming down the line. And that is the entirety of the thing. And with that, we can write Flash, and I've wrapped it all up into a couple of Python scripts. So I can copy something into Flash, read something out of Flash. The Python script is loading the 2 different programs in order to do these commands under the covers. It doesn't really make any difference on the outside that there's program loading involved. And it seems to work quite reliably. And the speed of writing is about 20K a second. So that's not bad. So sort of if you're writing 100K, you have to wait 5 seconds for it to load it into Flash. I think if you had a microcontroller, a genuine microcontroller, it could probably run 2 or 3 times faster than that. But one of the things you have to have before you can actually run an embedded microcontroller on the GA144 is a Flash image for it to boot from. So I think this is a necessary first step, that you've got to write Flash in order to be able to make a microcontroller. Okay, so that is how I did it. You'll notice in the diagram, I had a long serpentine path, and there was no way I was going to type in all those numbers because there were 33 of them. So I made a new source code utility to replicate a particular node and replicate it in a curve across the chip. So for example, for wires and for those recite nodes, and I now use it for everything, but for the first one, for 706 to 707, is a pair of wire nodes. And I was just doing those by hand, but it gets kind of tiresome, and it's also very hard to read. What does it actually do? So what I wanted is a node which was a utility for painting out those nodes in a particular direction. So what this plow macro does is I say I want to run a bunch of recite nodes starting on node 604, and input is from the south, and then going in the following directions. So I say 604 from the south, and then move west, and then go south 6, west 1, north 6, west 1, south 6, west 1, north 6, and then another north, and then east a few times over to the 705. So it's a bit like if you've used those very old tools for VLSI layout where you're painting something using relative movements. And this saves on having to type in all those node addresses and compute whether east or west is the next one. So they're all wired up together head to tail so that it forms a curve like that. Okay. Any questions on Flash? I will.
Could you have changed your algorithm so that after you got the things across the top 700 to 704, after say 702 gets to a certain point, it diverts things down to 602, and then after that it shoves things over to 701, which then diverts X number of things to 601. So instead of doing the serpentine thing, 70, I guess you go to 700, bring 6 things down, then 701 would say, I've given 706 things. From now on, I'm just going to do it myself.
Right. And that would cut down on the latency, I guess.
Well, also the number of cycles that you're running through Flash, because you basically, the serpentine thing means 600 things. The worst case is you got to put information 600 times. Of course, a 704 is always going to be stuck with, if you send 600 things, it has 600 cycles.
Yes.
Okay.
Yeah. But consider at the end of the run when 604 is dumping its contents, everything after that, up until that point, has turned into a wire node by that point. So it's actually relatively cheap. The bandwidth of a wire node is kind of fantastic. It's really quick. So they're all sitting on the read, trying to grab the next, and then instantly putting it on their output. So
if they're doing more advanced logic or counters in each cell, would actually be counterproductive.
Cost more code. That's what you're short of.
Okay.
yeah.
So in a similar vein, have you looked at other space filling curves that might have like a...
Could do, but they have to be simple 4-connected curves.
Okay.
So yeah, and I did originally think I was going to. There's plenty more memory here. I could have carried on going, but
Sort of space filling curve, but you said it wouldn't make much difference.
I mean, given that it's fairly easy to come up with a curve which uses every single node, then it's also. I mean. Yeah, for this Flash, I just actually needed to get the Flash written. And the reason I did all of this stuff instead of building a microcontroller and trying to make an arbitrary RAM is because I wanted the sort of the line of least resistance to get it done. So,
with the plow macro there, would the end be E5 then?
Yeah, could have been. Yeah, but I just shortened it to make it fit on the slide. So, yeah. I mean, it is a lot of words. It's just kind of this quite daunting thing, this plow thing, but it's a lot less daunting than 35 separate nodes with east and west and making them all line up. Okay, why are we particularly interested in writing to Flash? Well, what we want to do is make a virtual machine running on the GA144. That would be our equivalent of a microcontroller, which executes from Flash. There are other systems like eForth, which boots from Flash, but then actually runs from RAM. And we're quite interested in this sort of super low energy microcontroller virtual machine running on 605, which reads from Flash and executes directly from Flash. It seems that's kind of an interesting design point, particularly for very small embedded devices with no external RAM. You could imagine in just entering the science fiction scenario where somebody figures out how to make a large RAM, you could imagine 605 as a microcontroller and then maybe a 4K RAM sitting right here being proper memory. And then that's a perfectly acceptable general purpose virtual machine for running algorithms. So that's where we're headed, and maybe next month or two we'll have something going now that we can actually write images into the Flash. Okay, that's it. Well, yeah, it does dump the entire, but the Python script just stops listening when it reaches the point it's interested in. It's
maybe if you have like a gray code curve or a silver curve, it might be easier to read parts of it from, I don't know much about the GA144, but to read parts of it from another part, read like a subset of that flash with a shorter route.
Right.
If you had a gray coded curve or a Hilbert curve,
Yeah.
it'd be more amenable to that.
Right, and offer, yeah. In fact, yeah, one of those curves for random access. I mean, a shift register arranged like that would give multiple taps, and you could maybe, yeah. So, yeah, there's,
Gray codes are for, I guess.
right. Yeah.
Fewer less bit switching, essentially.
Right. There's a very exciting set of possibilities with the GA144, but yeah. Okay.
First saw that's a nice thing to do digital oscilloscope. Just like what you done, you see in 1940 it has that A-to-D converter there.
Right.
Then you just shift the data through and then stop at how many, however many points that you want to record. Once you stop it, then recycle the data then output the driver scope.
Right. I mean, and that's, so while I was still thinking, I mentioned I went through thinking about shift registers. If you hook a shift register head to tail, then you've got just what you need for a digital scope, right? You can tap it and then loop it, and you've made a memory but without any addressing, which is kind of nice, because all you'd ever want is to play back. So yeah. Yeah. Well,
Access is always on the edge, but what if they created a lattice, across the top, so we have two
right.
access, and the third is your plus.
Yeah.
Within the PCB or in the IC itself?
So we're not saying
Then it has its own, get in and out.
So with a blade line, the problem is that once you send the data, it's stored, but in the end it's lost.
Right. Right.
So you send a signal, you never get a signal. So if you kind of loop this blade line,
Right.
basically, you can send a signal, it will store it there forever.
Right.
And loop has a property of random access planning. It's this property from Neiman machine, which means if you wait enough long enough,
Yes.
if you make a loop.
Yeah, a loop of instructions. Because it would be executable. Right. Right. Right.
So you create a loop and sit on the loop, and the loop just
Yes. Okay.
you get the problem of random access memory in all sides of
Right. It's just a matter of waiting, timing.
and it's quick.
Yeah.
Right? You have ability to kind of stop that loop.
Yeah.
So the question and wait.
Right.
That's not a given. Okay, skip something.
Just a count. Yeah.
It's around.
Right. Okay. Who's next? A break? Okay. Thanks.
scuttlebutt around the Genealogy Institute is that Forth and Lisp have intertwined roots.
Oh, really?
Oh, yes. Oh, this Forth looks a lot Lisp. So you said Forth is a Lisp processor. By the way, check this out.
Oh, really?
Not even sure what I'm uncertain about. All right, so Tate's going to give us a quick.
Okay.
And then we're going to get into the scheduled talk. So
Mm-hmm.
we're off.
Okay. Thank you. Thank you. Yeah, I just want to show you my new website. Almost a year ago, I closed down feed.com because I said, oh, I'm not going to do any more work, and it's not making enough money, so I can't make my monthly payment. So I closed it down, and ever since that, I regret it. But then a couple of months ago, I went to babysit my grandson and his sister. He's about 10, 11. And he asked me, hey, Grandpa, do you have a website? I said, no, I don't. I used to have one, but I don't have it. And he said, yes, let me show you how to build your own website. I said, yeah, sure, why not? So he pulled out his dad's computer and fiddled around with it and said, see my website? And he told me that, you go to Google and do the sites, and then you can build your own website. And so he, at school, he built his own website and show off his project there. I was, yeah, sure, why not? So I went and actually get into the Google sites and open up, try to do my own website. And it's kind of limiting. The capability is not unlimited. It's very limited. But you can get a website, and if you actually want to do something independent of a pre-configured host, you pay $10 a month. I say, well, I used to pay $25 a month, so $10 is much better. So here it is. It's the what I did is just put all the documents and all the disks that I have over the years, and I just try to get things up there. Let me see, how do I? Okay, so here I have basically the first page has a summary of all the E4 system. So the E4 system has all this new and great stuff. The E4 2.3, I just put it down a couple of days ago, and ESP4 for the ESP8266, and then the other things. These are the more important, or I think things might be of interest to other people. So that's a system. If you want to go there, I put some documentation there. I can't put the whole thing there, so I just extract one chapter of it and put it there. Just show you some of the things that I've been working on. So, and some of the books there. These books have been scanned, either scanned or retyped in, or somehow recovered from electronic files I have stored on my computer, and all these books has been revised so they can access electronically. And I think generally I just put the first chapter or the preface on this website. So that's the books and the workshops. We have several workshops so far. So the CPU workshop, we do the EP16, EP32, the 8080, and also the PDP-1. So some of this information are there. And the fourth out is just some random thing. And I think this caught George's eye. Fourth is a list processor. So, okay, so that's my website. And I don't think you can read it's the sites, google.com or feet23.com and eForth, and I think the home, or home. So just look it up and see if you can access it. Thank you very much. Yeah, this is their the canned design. Yeah, it's very pleasant. But I can only go 3 levels deep. Okay, so that's the limit. You can't go anything after that. And I want to put all the PDF files and all these things, but I can't. Yeah.
You're limited to three levels, I presume, because it's a free version.
It's not a free version. It's I pay $10 a month. So, yeah.
Yeah. And then still only 3 levels.
Only 3 levels. And I still.
Of directories or?
Well, only 3 levels. This is the first level. You have home, and then you have these topics, and each topic you have a list of things, and that's the end. And I don't know how to put images, files in it, and the most important is I want the PayPal button there so people can pay for it.
I'm surprised. I know there are several programs. Even Apple had
Okay,
one.
Tig, are you done?
Done.
You got the speaker.
Okay. All right.
Yeah, the last time that didn't go so well. Yeah, I
learned a valuable lesson.
Yeah, I got a note from England. He says, "I watched your talk, but there was no audio." I know. It's like, all right. Just give me. I
haven't had that experience where I was flapping my lips.
Yeah. All right. So I've got a pile of demo stuff set up right here, so I'm just going to take it with me. Boy, that's convenient. Let's see. I need that. Oh, thanks. Is it? I'll keep it in the chair. Thank you. Oh, yeah, it's great. Thanks. Maybe a little further so I can see the screen. A little bit. All right. Let's see. All right. I just thought it was pretty. All right. Is there some way to get an audio check to know that it's actually working this time?
I am listening to your slightly delayed presentation.
Excellent. All right.
Because I learned that same lesson.
Yeah. So you all have seen a variation on this before. I don't know how much of it's public. I like to play with weird devices and build things out of them like clocks. I like making clocks. The device, am I staying there?
If you can move your table over there, then we can get the screen and your.
And me?
And, yeah.
Okay. So I should stand like over here.
Thank you.
Okay. So I'm an embedded systems hacker. I do it for a living too. And the interesting devices to me these days, this is an energy micro device. It's an ultra low power device. It's a pretty interesting market these days. There's applications like smart meters are making a lot of people excited. And then it's all about ultra low power. So this is an energy micro device. It'll run on a coin cell for years and years. And of course, what are you going to do besides put forth on it? So here we go. So this is the basic problem for all these embedded systems. You want to run forth on some chip, and you picked your chip. But this is what kind of happens. You go looking around, you find somebody who's already done forth your architecture. Then you find some demo that you like that you're going to rip up and hack up and save a lot of time. And then you're like, well, I need networking. And then it's like, well, these things don't match up. So this is kind of an interesting thing with FreeRTOS. FreeRTOS has some interesting ports out there that you can use as a starting point for applications. There's networking stacks. Well, but on your chip and your board, they only have a port to micro IP, which is frankly a crappy stack, and you want something better. So there's another way of doing things, which is you put forth into the mix, but you want to leverage a bunch of code. So here's a little background on the whole thing. A bit of a repeat. I ported Risky Pignus a long time ago because I like Cortex-M chips and I like TI's Cortex-Ms. I use them a lot. I work for a company that uses a lot of Macintoshes, and I like Macs because I'm an old Unix guy, and frankly, I hate systems maintenance, but I like my shell prompt. And then typically when you pull things up, configuring clocks on devices is an awful thing because it's very proprietary and it's poorly documented and it's a big waste of time. So in a lot of traditional forth applications, what you're going to do is you're going to take out the data sheet and you're going to start banging away registers and you can configure it all. And frankly, it's a big waste of time because it's already been done. The vendor has already shipped sample applications. They've shipped Hello World. They've got libraries. You don't want to do that all over again. So this is how it all came about. As I got to know these devices better, I'm like, hey, there's a system call there. Let's just use that. We'll have an abstraction. It's a BIOS. And onwards. So this has all been evolving over time. For really tiny base systems, I've played around with some launcher implementations. It's basically a bootloader. You can do something like you can write a piece of C that initializes the machine and then hands it over to forth. So forth starts up, and forth doesn't have to do any hardware initialization at all. It's all been done. So your UART handler just has to understand like where the status bits are in the UART register. So it's a very simple approach. The other thing that you have to do if you want to do more sophisticated applications is you have to have runtime linking between the C environment and forth. So your C environment is going to, for instance, have an interrupt handler, and it's going to get a UART byte, and you want forth to get it. So forth has to know where it is. So that's what's going on. So I'm going to move along because you guys have probably seen some of this. This is what I've been doing the last couple of years, minimalist ports. System call handler's gotten a lot cleaner. I actually have MPU support on my platforms. If the forth shell steps out of its sandbox, it gets whacked on the head and it restarts. It's a very handy thing if you access non-defined memory. So your system doesn't crash and go off in the weeds. You actually get a fault dump and on you go. I poured this to a bunch of platforms at this point. So it's largely binary compatible. You guys probably know this, but key points on the Cortex-M, there's a whole family of them. They're taking over the world. Etsy. Some things that kind of feed back into this architecture that are good to be aware of. The architecture, one of the most innovative features of the architecture is an interrupt controller that is very thoughtful and well designed. It's very low latency. And the thing that's really interesting about it is it stacks the registers in a way that's compatible with C, which means that interrupt handlers are just C functions. They require no preambles, no headers, no nothing. You just write a void function, and that's your interrupt handler. You're done. Bang. It's got user and supervisor stacks and memory protection. It's etc. And then this is where working with Forth gets kind of interesting. It turns out that interrupt handlers for Forth on this platform, on this architecture, are kind of painful because Forth can't do anything interesting without its stacks environment and its user spaces. So an interrupt handler on Forth is actually messier than it is in C because Forth has to set up a data stack. The return stack comes for free because the interrupt handler does it. It's got to set up a data stack. It's got to set up a user area. And then it's got to have the arrangements to share these things between handlers. So actually, interrupt handling on the Cortex-M is messier in Forth than it is in C. So the answer is, well, we'll just use C for the interrupt handlers. Right. Yeah. Machine initialization sucks. So it's already been done. Use their code. All right. So where are we going next? Right. You guys know all this. Forth, I test unit test in Forth all the time. You can directly access the memory and then bang, wham. You know these things. So I've been working with MP for a couple of years. I like it because I'm lazy and I want to just buy something and use it. So this is kind of my standard pitch for MP's really nice stuff. It's a compiler system, so the code that comes out is really fast. It's very, very tight, good stuff. The documentation is awesome. It's all there. I guess when their customers call with questions, they would just write more documentation because it's all good. They have hobbyist compatible products. There's like a light compiler that's very minimal and is plenty big for embedded stuff that most people do. You know. So anyway, let me talk about how this stuff all fits together. The thing that this all sits on top of is ARM's procedure call standard, the ARM architecture procedure calling standard. And this is a well-defined thing. It defines how registers are used for function calls, exactly what they do, etc. And to get back to what we were talking about a moment ago, the Cortex-M stacks registers in a way that are compatible with the ABI. So it's really slick. So for instance, this is how you call a piece of C from Forth. You basically you take the thing off the top of the stack, you put it in R0, you take the second thing off the top of the stack, you jump, you do a little math, bam. That's how you call a C function from Forth on Cortex-M. This is on the web. So the other thing, the Cortex-M architecture has a really clean architecture, a really clean interface for system calls. There is a system call assembly function service. And the service vector takes an argument, which is an 8-bit integer, which you'll see right here. There it is, bam. So this is a little slice of Forth that does essentially a BIOS call. That's all it takes. It's pretty small. So anyway, this is the what have you been doing lately part. So I've been pointing to these little boards, which has been a chance to pipe clean everything, make it all clean. And this is basically how you do it. So I'm going to go through kind of how you make all this happen, how you start with a raw device and you stick Forth on it and use all the existing stuff. So the bottom line, because Forth is ultimately about interactivity, you need a UART. I'm going to go through these same things apply with USB. You can do similar tricks with USB demo applications. You can find the spot in the USB code where it actually hands off the data to the UART, and you can stick it in a FIFO instead. And bam, instant USB connected Forth. So yeah, you start, every vendor will give you a pile of demo code, And somewhere in there, there's going to be hello world for the UART, and that's where you start. So you take their existing stuff, and then level 0 is you write forth drivers that don't have the hardware initialization. They just know about the registers. They know where the FIFO full bit for the UART is. They know where the FIFO not empty bit is. So you can pull that kind of thing. So there's multiple levels of this stuff. Here we go. Yeah, this is about as thin as it gets. This is what I'd call kind of a launcher approach, where the C is basically a bootloader. So here's the fourth code for serial emit, which is MP uses a stream model, which is for every stream there's going to be multiple consoles, for instance. So for console 0, everybody has to implement a serial emit function, which is given a character and a vector, out it goes. And this scales really nicely because you can have network attached devices. You can have USB attached devices. It's basically a stream protocol. So you basically implement these simple wrappers. Here's what it looks like on a really simple device. In this case, you're going to pass in the base address of the UART. And we're going to make 2 copies. We're going to take the status bit. We're going to pull it. You're going to AND it. I forget what this is. Oh yeah, here's the register. I think that's, yeah, buffer low. I forget what it stands for. Yeah, the full test. And then yeah, you're going to spin on that until there's space free, and then you're going to send out the UART. So that's it. That's your basic minimalist fourth output code. So this all led to a lot of crazy. It started with Energy Micros has all these kind of spiffy tools for measuring power consumption. So we start writing the code, and it's like, wow, look at this. We're using, what is that, 3 milliamps on a coin cell device? That's kind of awful. This is what happened when I dumped things. It got bad. It's okay, we'll turn on the clocks. Okay, you turn on the clocks, it gets better. The way all these devices work is they have a 32 kilohertz crystal, and they spend all their time kind of laying on the floor in a 32 kilohertz crystal mode, and then something will happen. They wake up really fast and run code. Well, we'll just run slower. That gets better. Next level, of course, architecturally, there's this feature on the Cortex-M called Wi-Fi, or wait for interrupt, Wi-Fi, people call it. People talk about this, in the hallways. Now we Wi-Fi. So basically, Forth can Wi-Fi the processor in its loop, and the thing that's really slick about this is that the processor is going to wake on an interrupt event. So all you have to do is have your peripherals doing their normal thing. They wake up. So when somebody hits a UART character, you get an interrupt. The system wakes up. Forth continues. It's very simple. So you need some shared data. That's when you do the bootloader approach. You have an interrupt handler that accepts the character and it sticks it in a known location in memory, and then Forth wakes up and says, oh, hey, there's a character there. On we go. So that's one way to do it. Let's see. Yeah, I'm gonna skim along. There's many ways of Forth and C sharing data. There's a number of ways to do it. You can, for instance, pass it in when you crank up Forth. I mean, this is, let's see. I'm leaving out some background that you need to be aware of. The Forth application is going to be a normal Cortex-M application, which means it's going to have a stack pointer and an initial program counter. If you know where it is in memory, you know how to start it up. And you can just pass it some data. So that's one approach. You can have a piece of C, and it's going to pass in the address of where this little shared blob of stuff is. And then Forth comes along, and it grabs it. Here's the code that this is the very first code that runs when Forth starts up. It initializes some stacks. Here's let's see. Oh yeah, right. That's the return stack pointer, and then here's I'm brain locking. But anyway, at some point you got to call you call the interconnect, and it harvests the thing that just got left for you in your function call. I'm not going to get into that right now, but it's available. There's other ways to do it. So here's what it looks like in practice. Let's see if I can get a pointer going somewhere. Where is that? Nope. Oh well. Do we have a pointer? No. Anybody have a laser? Oh, excellent. Don't shine that in my eyes. So this is what a minimalist one looks like. You basically have a UART. You have a UART interrupt handler that responds to a UART and then sticks it in a shared memory location. Yay! Thank you.
The green button there with the
Thank you.
vertical line.
All right. Yeah. So here's what it looks like in the minimalist case. The serial key function basically just looks in this space, and it looks for it to be something besides -1. And then so this is the most basic loop that you use for low-level I/O, which is that you're going to look for a character, and if there is not one there, you're going to call the scheduler, pause, or yield, whatever, and then otherwise you're going to Wi-Fi. So this is a really efficient way to do things. You just basically keep polling. This, by the way, is disable interrupts. So you keep looking for something to be in this little location in memory. When you're done, you pull it out, and then you return it, because SEER key is going to spin until somebody hits a key. So when you start doing things like this, your numbers go down. We're below milliamp now. One thing that gets kind of entertaining, on this part, you have to actually tell it that when you use Wi-Fi, it needs to go into an ultra low power state. So this is what you get without working very hard on this platform. You get 14 microamps steady state, which is a pretty good start. All right, so let's talk about things that go wrong. So here's a couple of things I learned in my most recent attempt to make this happen. One of the things I'm going to get into in a little bit is about stitching binaries. So these are things that kind of go wrong. On any embedded platform, you're going to need some kind of tool for injecting an image into the device, the flash programmer, whatever it may be. Sometimes they don't do what you expect. There's some programmers that are better or worse at, say, load this chunk of memory, then load this chunk of memory. If you're using, say, GDB does not really have a clear concept of put this in this memory and this in that memory. It basically wants to just throw it all in there, which we'll get into in a minute. So we're going to talk about stitching, and it's an important thing to understand how to do, because it's critical. The other thing is that when you're working on low-level I/O, it tends to go wrong really fast. So the trick is to do as little as possible in every iteration. So typically, what I do is I'll start with a piece of C that initializes the hardware and simply says hello, and then you write the piece of code that is the wrapped call that you test that, and then you write an echo test. And once you've got echo working, then you can splice in forth, and forth can actually interact with the rest of the system. So I can get into more of that. People are curious about bringing it up. So if you want to take it to the next level, tasks are a really wonderful thing in the forth environment. Everything is event-driven, so it maps really nicely. You can have a task that maps to an event. The other thing that's really important is that when you have a multitasker, you have a very clear concept of whether the system needs to be awake or asleep. And then the tasker can essentially put the thing into an ultra-low power state. So the other thing I've found from implementing this recently is that when you can block things, the code gets simpler. You don't have to keep state. You just, you write to the UART, the FIFO is full. Well, you just block the task, and then life goes on. The one thing that tasks are cheap on forth. You barely need anything. So one of the things I did is MPE supplies a multitasker. I've just been using that, but I've made some improvements to it, so it's actually more efficient. For instance, I use what's called lazy register stacking. It's pretty tempting to write a multitasker that simply stacks all the registers and then finds a task and then unstacks them. That's not what you want in an ultra low power system, because typically what you're going to have is a situation where almost everybody is asleep and you're going to run one at a time. So you don't want to actually stack the registers and that kind of thing. You want to design things for efficiency. So this is basically the setup and the logic. You look for the next task control block. You see if it's runnable. You remember where you started, of course. And then you just keep running through this loop. So you run through the loop and you say, look at the next task. Is it runnable? Okay, well, no, it's not runnable. You see if you made it all the way around, because if you made it all the way around, there's no work to do. And it's time to go into a low power state. So all you have to remember in this task loop is you have to remember where you started. So every time you run around, you say, well, did I go around the loop? If I made it around, nobody ran, well, time to go into a low power state. So your system is going to stay low all the time. So if you find a runnable task, you figure out if you're where you started, because it's possible that your task started up. If you've come around the task loop and you've come back to yourself, there's no point stacking the registers. They're right where you left them. So you just go back. So that's kind of the same. You could do this with long jump too. Likewise, if you found somebody else, okay, well, now we're going to stack a bunch of registers, and now we'll do an actual context switch. So this is fun. Anyway, there's the code. Next. This stuff is all online, by the way. It's all up on GitHub. So please feel free to steal it. That's what it's for. Yeah, okay, so here's the next problem. How do you wake things up? If something can block and go to sleep, you're going to have to wake it up. And the thing that gets kind of strange is everything has to be thread safe. It's going to be bad. So there's this little race condition you have to deal with where Forth says, hey, here's a character, and the service system says, sorry, I'm busy. And then Forth would then have to say, go to sleep and call pause and all that. But what happens if the space frees up after you have already gone to sleep? And the short answer is you can't let Forth actually manage its own task states in these cases. You have to let the supervisor do it. So the next step of this is that when you do a system call to like do an emit, you've got to pass in your user pointer so you can be put to sleep by the operating system. So that's actually, otherwise you get these kind of interesting hazards. And a lot of effort is put into not letting these hazards ever happen, because there will be nothing but heartache if your interrupt handler is clearing a bit that you set. It's just very bad. So we'll get back to sock puppet again. As I mentioned, the system call interface is really clean. One of the things that's kind of interesting is it's a binary application programming interface, so you can actually take the exact same Forth environment that you ran on one chip and run on another chip. Maybe you have to change the location in memory, but I've done this before. I've literally compiled the exact same code and run on two completely different chips, and it just worked. It's completely possible. You know, it's kind of like a BIOS. So part of what I'm going to give out today are some kind of key tool bits that used to make this all happen. And once again, they are all on the line. They're all online. This one's on GitHub. This is a system call handler, and this is largely a direct ripoff of things that you'll find in any introductory book on this chip. This is basically how it works, and I'm not going to. If people are curious about the specifics, we can get into that afterwards. The thing that's different about mine is I just assume that everybody wants all their arguments. So in earlier versions, you would have system call handlers that would have to like pull their arguments out of the stack, and it was a mess. Now I just assume that everybody gets their 3 arguments, and that everybody's going to return 2 things. So now it's all basically a big table lookup. I'm going to give you all just a brief aside here. Here we go. I'm sorry, I don't have it. So, just a moment. All right, well, onwards. So yeah, here's what a system call handler looks like. It's this is a function. It's just going to go in a table of system calls. You're going to have up to 256. Bam. In this case, there's this concept of streams in the MPE world that there's 0, 1, etc. So you can have multiple UARTs, and then basically that's what it looks like in practice. You have a wrapper that dispatches things. It could be dispatching it to UART or to USB or whatever. So in terms of getting things up and going, the interface defines 16 reserve vectors, but to get functional, you only need 3. That's all it takes to get interacting with your device. You need key and key query, or how do we pronounce question mark? I don't know. And then put car. And then one of the things, the spec defines character turn and type, which makes sense on some platforms, but you can actually emulate them. If you're trying to go really fast and produce a lot of data, you can implement things like type, and that will reduce the system call overhead. There'll be fewer of them. So onwards. So the other thing is that if you're going to do a high-performance system, your drivers need to have state. So this is essentially the classic example of how that's going to work. This is an excerpt from emit and from the system call that supports emit. So everything is going to go into a ring buffer, and at some point it's going to get full. And then, so this is what it looks like. If the ring buffer is full, then you remember the task control block of the thing that was asking you to do the work. And then you say, hey, they're blocked. And if they actually sent you one, you stop their thread. That's it. It's that clean. So we're gonna, so in this multitask environment, it's a pretty simple status bit. You're basically runnable. There's messages, events, etc. Onwards. So in terms of bringing these things up, and this is advice for him, you start very small. This is a little snippet of code that I've used in everything, and it's basically, a static. You guys, everyone can read. It's basically you just take a character string and you start with the function call that is provided by the vendor. And then when that works, everything is good. And then you move on to your own thing. And when that works, well, okay, now we'll use the actual system call and we'll make sure that works. And then typically what I do then is I don't actually launch Forth yet until this stuff all works. And then Forth can actually interact with the system calls, and I know that they work. But I'll have another one that does an echo test, that it does, while get car, put car. So then you can test the pipe all the way around, because there's frankly no point cranking up Forth unless you actually have a working console. You're not going to get anywhere. So that's how it's done. So when you actually do all the sleeping correctly on this chip, you can get down to under 10 microamps. So this little, what's that? So what you're seeing here, the benchmark I use is I dump out the first 256 bytes of memory. So what you're seeing here is that this part is idling around at well below a microamp. And then this is me interacting with it on a serial console while it's in this state. So well, here we go. For instance, this is my device right here. So this device is, currently running, under a microamp. This is my basic benchmark. I'll like that better. So that little spike that you saw on the other screen is that activity right there. And otherwise, this device is idling at under a microamp. But yeah, you can do this while it's running off a coin cell. This is a very clever device. It has what's called a low energy UART It runs off a 32 kilohertz crystal.
Consider using this in IoT?
That's what it's for.
Okay.
Yeah.
You didn't mention it.
Yeah, it's
I want to add you.
these are
This is perfect.
these are tools.
Yes, this is great.
Yeah.
Because you can also substitute your coin cell with whatever large.
Right. Potatoes for bonus points. Yeah, you could definitely. I don't know how many years you can get out of a potato though, because at some point biology might play a role.
Yes.
So, all right. More about things I learned the hard way. I don't know how many of you have experienced this. Sometimes your programmer is not loading the thing to the chip that you think it is. I don't think I've.
20 minutes to find.
Yeah, I don't think I've wasted less than 30 minutes on that mistake ever. I'm like, wait, this is not what I thought it was. So the other thing I want to run through quickly is how to stitch the binaries. If you're doing a mixed language environment, you're going to have to combine these images. And your programming tool may or may not be friendly with put in the top half, put in the bottom half. You're actually better off just stitching them together and having a combined thing. And there's a bunch of ways to do it. And I'm going to show you all the magic secret sauce for them that apply here. So you can just steal it all and just use it. This was a hard one to learn. Fourth, well, it depends on your implementation. I ran into a lot of really evil bugs because Forth did not have initialized memory. So,
It does. It's called cold.
Right. Well, the cold on my.
Yeah, it wasn't written yet.
Well, no, I've got all that, but the cold on this on MPE's cold does not do that. I wish it does, but it was very easy to fix. I just zap all Forth's memory before I launch it, and all is well. MPE is a complete. It's a commercial product. It's very capable. A standalone Forth is about 24K or so, just out of the box. So you can hack stuff out and you can get it way smaller. So I did that. The other thing is that memory gets really tight. Tasks are about 500 to 700 bytes a piece. By the time you get a user area and a return stack and a data stack, it starts adding up really quick. And the next thing you know, so you got to be thrifty. So let me talk about stitching. Then we'll do more demos. You got to partition everything. And I'm going to go really quick here. There's a couple of ways to do it. You can write a shell script. It's online. Basically, you can do a little shell magic and measure things and then play with DD. Bam, that's one way to do it. The other approach on this platform is you can have MPE do the stitching. You can have MPE pull in the bootloader and bang, it's in there. This can be good because if you use an Intel hex format, it includes addressing information, and it'll probably work better. There's multiple ways to do it. If you're running on an NXP device, there's this piece of software called SREC that's very handy for these things. It knows how to do things like generate checksums if you have a micro that needs a checksum. And I've done this on some of the bootloader things. It understands concept like pull in the hex file for the Intel the Intel format hex file for the launcher. So here's what it looks like. So take the launcher, whack off the end. I forget why we do this, and then pull in the actual Forth image and put it here. So that's the other way to do it. The other trick, I have been working lately with. This is a Black Magic debug probe. It's an open source debug probe that's frankly really nicely thought out. It's a GDB server. So you talk to it with GDB, which I've never been a big fan of, but it works. But GDB does not understand binary files very well. GDB likes object files. So what are you going to do? Well, the answer is you do a little cleverness with your linker file, and you create a magic section. Like, flash, this is where Forth is going to live. This is how big it is. And you define it in your linker file, and you say, okay, the Forth stuff goes into flash 2 here. And then later in your build script, you're basically going to say, here's how you do Forth.0. And the answer is you obj copy it using some magic foo. And you rename it. So the dot data goes into the dot Forth, and magic, bang, you're done. So we just built an ELF binary that includes a big slab of bytes. And now GDB understands this. And we've been talking about various things with vendor tools. Sorry, redundancy. Let's see. We're going to do demos. Okay. So. Yeah, I've been trying to capture a lot of the hard-won knowledge, and this will all be available on the web. Yes, this time you'll get the slides because they're done. All right, so let me start dragging things over here for you. Let's see. All right. See if I can see. So here is just set it properly. I start dragging windows where I can see them. So here's my environment. So this is the Blackmagic debug probe, and it implements two UARTs, one of which is the GDB server, and the other which is just a plain old UART. So the build process, in my case, looks like this. If I can, there we go, just a moment. Lost track of my windows. Okay. So in my case, I just built a build script that descends down into the C world, does a make, and then it combines the pieces. So like in this case, it took the supervisor, which was almost 8K, added 60 bytes of padding, and then stuck. In this case, the fourth image is actually 24K. It could probably be slimmed down more, and it's just barely under the wire. So the end result is I get a stitched image, and then I run that through the magic obj copy stuff I showed you guys, and you get this thing called package.elf, which is, your basic package file. So I'm going to crank up GDB, and I'm going to feed it the ELF file, and it's going to understand that. So now I will crank up my cheat sheet, because I can't remember all this stuff. Here we go. So I will connect to my probe, and then I'll say monitor. So I'm going to tell the debug probe to use single wire debug, and then look at the devices. So it's going to scan the bus. It found my device. I attach to it, and now I can I can stop the device. Look at registers, etc. And you'll notice the fourth, of course, over here is dead, which I would expect it to be. So now I'm going to have GDB load up my binary into the device. Off we go. So now it's loaded, and I can just say run, and then bam, instant fourth prompt. So that's the basics of how you use this open source tool to make it all happen. So in terms of things like tasking, here's a basic program. I can say, okay, let's so we can take something, takes in messages, reset it, and then so here's a basic task in this environment. We'll call it emitter. I'll just saw overflow because I don't have software flow control working. So here's a word, and then I was talking a little bit ago how to have vectored I/O in this environment. This is the output vector, and I'm going to say, hey, send it to the console, because when you start a task, it has no concept of where its I/O goes. You have to tell it. And then, so tasks have to be infinite loops. So we'll just add something pretty basic here. So what I'm going to do see, is we'll just have it pull a location in memory. Pull in the message variable. If there's something in there, emit it, clear it, do it again. And then after that, we're going to pause, or some people call it yield. And then we're going to do that again. Bam. Okay, so I've defined my word. So then here's how you do tasks in this universe. You define a task. I say, okay, we're going to take this emitter and we're going to attach it to foo, which is my task, and we're going to initiate it. So now I have a background task running. There it is right there. So here's my task. These are existing stuff because this is actually a clock. And then, so now I have something where I've got a task that's spinning in the background. It's pausing and waiting. It's sucking down a lot of power because this is a naive approach. And we can just say 40. So I'm going to stuff something into the variable that's watching, and bam. So the task woke up, saw my character, sent it to the screen. A is 41. There's my A. So that's what a task looks like. So the other thing that came up was MP. These demos are with MP's light compiler, and it runs under Wine. So this is what the process looks like for these guys. You have to include a control file. These things are all published. You crank up. This is MPE's light compiler that you can just go get off the internet. So it compiled all my code. You know, here's all the words that got defined, created, etc. Colon definitions. I forget all their syntax. Yeah, here's an equate. It's a compiler level thing. Yeah, here's a value. So here's all their stuff. And then you can see up here, you know, here are things that I have written. Like here's something that does some basic math. So you can do things like, you know, so you can, you know, disassemble your code, look at what's going on, etc. And when you're done, you run by, and out comes an image, and then you build it into, you put it together. So that was the part that I actually kind of misled you guys about. When I ran the build, I already had an image, but that's basically what it looks like in practice. So, any questions?
You had to write your own code to call object file. Is that right? I think I remember. So you could call an object. Yeah.
So I could call a piece of C from Forth?
Yes.
Yeah. So yeah, that stuff exists. I have published it all, and then in MP's commercial offerings, they'll generate the stuff for you. Let me just find that.
Well, the reason I'm saying is that's similar to what I had.
Yeah. Let's see.
I deleted the port of G4,
Yeah.
to G4.
Look, there it is right there.
Yes.
So so I basically just define a couple of words that do a little bit of stack manipulation and then jump to the C.
Yeah, what's nice is with G4, you can not only can you call and just go out and grab object code and bring it in, but you can also do dynamic linking.
Yes, that's a nice thing.
That is, like I said, it's unbelievable. Because once I got that, then because I did give a demo here, I think it was last year. No, it was 2016, early on, where I actually showed. I wrote. I had one fourth word that I spawned off several times, had it run, and I was also able to get all of them. I should do that again. Where I give the demo where it shows all the pthread calls.
Oh, nice. So I have published stuff that does a dynamic linking thing where I create essentially static tables of C, and then there's forth code that goes to the table, and it creates forth words that go with things. So you don't have to go find addresses. You just say, function call X, call 0 in, 0 out. Yes?
Could I ask you and other speakers to send Dave a short thing with links?
Absolutely.
Here's where to go to get started. Here's my
Yeah, I would be glad to. That's why I'm here.
Slides,
Yeah.
any of that stuff, send it to Dave for the meeting
Yeah.
notes.
No, I've been working on this for years. I want to see people use it. So, anything else?
Like I said, I just want to give a little thing. My goal of getting G4 hooked up with the RTOS got a little closer. I was trying to use NutX, but I think the guy Nut really is a nut because the code that calls, because what I need is red local storage. It looks like it's not being compiled in, but
RTEMS is still around.
yes, it's still around, and lately they said, we've just added thread local storage to version 4.12, but we haven't released 4.12, and I'm going, son of a bitch!
So what hardware are you running on?
Oh, it's gonna. I do it on x86.
Okay.
That's what I just initially want to get going there.
Yeah.
And then I want to be able to try it out on a Raspberry Pi.
Cool.
And there with the Raspberry Pi, then I can come up and make my own USB hub.
Absolutely.
How about that, Tane? Hubba hubba.
Cool.
Which means, yeah, but here's the thing. I would do the software implementation of what a hub chip does.
It can be done.
Okay.
Cool.
Because that encompasses not only host, but it also encompasses device. And it'd be nice to be able to create your own USB device and put the code in forth.
Nice. Anything else? Thanks for your attention. I'll send out a pile of links for you.
I learned a little bit more in the break with HDCP, which makes me very sad and paranoid.
Yeah, it should.
It seems that there's a certificate verification process between these devices, and they've gotten more aggressive. So I'm actually less hopeful that I'm going to find a device that will certainly permanently, but even maybe temporarily, circumvent it.
You have to take more steroids. Become more aggressive.
But here's the part I wanted to share because I find this ominous. Chromecast is obviously downloads updates, and that's how it gets revoked certificates. But your other devices, guess how they get updated? It turns out when you buy your DVDs and Blu-rays, they include on those DVDs and Blu-rays revoked certificates, so that you thereby disseminate out to everyone the revoked list. And so the mere act of playing these movie virus. Quite the opposite.
Well, actually, you're talking about a actual DVD player, right?
Yes.
Then it will take that list, update its internal RAM.
Yes.
But if you play that on a memory player that's inside your PC,
Yeah, there I'm assuming that the updates from Microsoft or wherever your OS vendor is.
Yeah.
Right. And nor do I don't at least have the impression that the protocol hops across. That is, if you have one device with an updated list, it does not update its neighbors.
especially if they're not connected.
The question that I sort of started wondering about, though, is that apparently now, as I said, the keys have been cracked with this scheme. And the keys are also used to digitally sign the revocations. So one does have to wonder if clever soul were to, for instance, send out a list of revocations that they could cause a list of Although, unfortunately, it also sounds like there's a new version of the protocol that's tied to the high definition that is at 4K displays. And so for those, they reset the keys and start it over. Well, this time I'm sure people. Makes me want to get his info back.
Oh.
So that's it, Dave. If you move the table, put it back where you found it. There are little marks on the floor, believe it or not, or they go seeking among you.
We got anything else, Kevin? Are we done?
I'm done.
We're done? See you next month. See you next month, folks. Bye.
Subscribers. Yay, Dennis!
Yay. We're 102.